Let's take a look at the products here. So, this is what type of reaction? This looks like a metathesis double replacement. So we just switch these. So we're going to have lithium ions with phosphate. So lithium is a +1, but phosphate is not a -1. Phosphate is a -3. And so how many lithiums are we going to need? We need 3 lithiums. Get Li3PO4. Do the correct formula. Okay, you shouldn't write charges like this here. If you wrote a charge here, nobody would know how to name that. Li3PO4 with a 3- charge, because it doesn't exist, right? So you don't write the. If you need charges to help you figure it out, write it somewhere else and then show it here. That's the formula. So we get lithium phosphate. What's the other product? Sodium sulfite. And the formula for sodium sulfite would be Na2SO3. And did you get driving force? Lithium salts, soluble or insoluble? Yeah, all lithium salts are soluble. In fact, all lithium and sodium salts are soluble because those are group 1 salts. So group 1 salts are soluble, no precipitate. How about gas? Either of these gas? Like carbonic acid, decomposes into gas, or maybe, no, those are salts. What else do we look for? Acid. And so, are we going from stronger acid to weaker acid here? No. Nothing's really changing here. And so what we see is there's no driving force. Therefore, we say that there's no reaction. No reaction. But we have to be careful of what we mean by no reaction. Because how many different reactions occur in nature? You think of all the chemical, that includes like biochemical reactions, industrial reactions, and whatever else. You think about all the reactions, there's so many different reactions going on every day in the world. And so how many different reactions are there? Maybe too many, too many to count. And so we try to classify those into simpler categories. Like how many types of reactions are occurring? How many different types of reactions are occurring every day in the world? Well, you could look at, this is why I didn't subdivide it the way our book did, because you could look at the types of reactions that our book has, and that's fine. There are quite a few, except the problem with that list of reactions is it's not comprehensive. A lot of reactions are omitted out of there. And so rather than narrow down and focus on the categories that the book does, the book talks about double replacement reactions, which is good. But I don't call it double replacement, I call it, what do I call this? I don't call this reaction a double replacement reaction, I call it a metathesis reaction. You know why I call it a metathesis reaction? Because double replacement is too narrow of a definition. Because if there's double replacement, then I have to memorize a whole bunch of other patterns, which makes it too much. And so rather than just learning one pattern and then missing a whole bunch, we'll call it metathesis, and we look out for certain things. But metathesis is a type of reaction. What other types of reactions are there in nature? Acid-base is another type of reaction. Oxidation reduction. So there are 3 basic types of reactions: metathesis, acid-base, and oxidation reduction. And so what we have here is this. We have to be careful because this is no reaction for metathesis. Because in metathesis, what are we looking for? We're looking for ion combinations, favorable ion combinations. But is that the only type of reaction that occurs between species? No, it's not the only reaction. There's also acid-base and redox. And so, so we see that there's no reaction for metathesis, but we should check for potential acid-base and redox reactions. Because there could potentially be a reaction here, it's just not metathesis. And so how do we deal with acid-base reactions? We'll look at that next here. For acid-base reactions, there are actually three definitions of what an acid and a base are, starting with Arrhenius. Arrhenius is the earliest definition of an acid and base, but it's too narrow. It's way too narrow of a definition. So there are a whole bunch of acids and bases that fell outside the Arrhenius definition. Arrhenius defined an acid as anything that gives H plus in solution, and a base is anything that gives hydroxide. But since it was too narrow, then we have to memorize a whole bunch of other categories, which is too much of a hassle. It's better just to broaden the definition. And so the first broadening was by Bronsted-Lowry. Bronsted-Lowry defined acid differently. Bronsted-Lowry defined acids as proton or hydrogen ion donors and bases as hydrogen ion acceptors. But it turns out that the Bronsted-Lowry definition is too narrow too, because there are some acids and bases that fell outside that definition. And so the definition was widened to capture, and this is the most comprehensive definition. The most comprehensive definition is Lewis. So Lewis is the current definition. This encompasses all acids and bases. However, the way we visualize Lewis acids and bases is a bit different. There's something called an electron pair, which we'll talk about later on, but acids are electron pair donors, or no, not donors, acceptors, and bases are electron pair donors. And so all we need is one definition. So we can get rid of Arrhenius, which is too narrow. Get rid of Bronsted-Lowry. Even though double replacement's a little too narrow, so I don't just say double replacement, I say metathesis, because metathesis, you'll see other patterns that fit the same type of reaction. What type of reaction? Favorable ion combinations. It just doesn't fit the AB plus CD pattern. So the same thing, we still can use it. So for example, we still can use Lewis, but then we can narrow it. Maybe we can isolate it to a subset of acids. If we isolate it to a subset of acids, then we can have the Bronsted acids. And what we're going to do is, we're pretty much not going to deal with the Arrhenius. Arrhenius is way too narrow. And the reason we're going to retain Bronsted-Lowry is because Bronsted-Lowry is a lot easier than Lewis to deal with. And so we're just going to look at a subset of acids, the Bronsted acids, initially. Later on, we'll widen it to look at all acids, Bronsted, whatever. And so that's okay. Some acids are going to be missing, but it'll be a lot easier. And so for Bronsted acid-base reactions, these are called proton or hydrogen transfer reactions. So we transfer one proton, H plus, from the acid to the base. The method is, if we want to make a prediction, transfer a proton to the acid base and determine if there's a driving force. The driving force is going from a stronger acid, which is less stable, to a weaker acid, which is more stable. And then, we could determine if further reaction occurs, like step 2. And so here's the method. The method is we inventory. So let's say we're interested in this You know, we see that there's no reaction for metathesis, maybe there's an acid-base reaction. And so how do we handle it? Well, the first step is to inventory. Inventory is to figure out what the major species in solution are. You know? So if we have a combination like this, then we figure out the major species. You know, these are aqueous. And so when I look at this salt over here, lithium sulfite, what type of structure do you expect pure lithium sulfite to have? Would it be molecules or would it be a lattice? A lattice. This would be a salt lattice. Do the crystals, when you put the crystals in water, do the crystals stay in water or do they get broken apart by the water molecules? Do the water molecules tear apart the crystal and dissolving it, or do the crystals stay together when it dissolves? What happens when, did I show you the animation? I didn't show the animation? Here's a sodium chloride crystal here. When that sodium chloride crystal is dissolved in water, what happens? Did I show this one or not? I showed this one? What happens is the water pulls apart the lattice. What's it apart? And so eventually what you're going to have are you're going to have the dissolved ions. So there goes a sodium ion there. Here goes a chloride ion there. So eventually that crystal is going to be completely, and you can see what's happening in the crystal here. Here they're just removing all the water molecules. So you can see how the water is pulling apart the salt lattice and getting it dissolved. And so in solution here, we don't expect any crystals, we don't expect any molecules of lithium sulfide. Instead, what we expect to find are the ions. And so what ions are going to be found here? We're going to find lithium ions and sulfide ions. All right, so this is part of the inventory process. When we inventory this, we're looking at what species we're going to find here. And so if I have lithium sulfide, I'm going to find lithium ions, sulfide ions. If I have sodium phosphate, what am I going to find? Sodium ions and phosphate ions. And so here's an inventory of the major species in solution. The major species. There's one other major species. Do you know what it is? Water. There's a lot of water around. Even though water is the solvent, water can actually react as a reactant because there are certain chemical properties of water that react. Okay, so we inventory. This is called the inventory here. And then we determine the strongest acid and the strongest base present. So, take a look. To determine the strongest acid and the strongest base presence, we're going to look at this chart here. This chart's on Piazza. And this is the acid-base chart here. So we see the strong acids here, the 7 common strong acids. Here. And then these acids are weak down here. but they get weaker and weaker as we go down the list. And so what's the difference between a strong acid and a weak acid?
Water, strong acids, and strength.
Yeah, that's what do we call that? We call that the leveling effect. What's the cause of the leveling effect? The cause of the leveling effect is this. All strong acids lose the H plus easily. That is, if you have a strong acid in water, the water can easily pluck off the hydrogen ion. This is the cause of the leveling effect. The cause of the leveling effect is this. Let's say this is an apple tree. And so strong acid would be like an apple down here. You know, some of the apples are easier to pluck off the tree than others. But all strong acids are easily plucked off by, let's say, this person here. They have a ladder. And so, of course, this is the easiest one here. So this is like perchloric acid, right? But this one's like hydroiodic acid. It's a little bit harder, but is this person going to have any trouble plucking this apple off? No. In fact, for any strong acids, and this would be the weakest of the strong acids. What's the weakest of the strong acids? HNO3? HNO3 is a little bit harder to pluck off the H+, right? The H+ being the apple here. But still, no problem. Because this person can reach, they just have to reach a little higher. Right? So this is the meaning of the leveling effect. We hit a certain level, you know, from this level below, all the apples are going to be plucked. And that is, from this level and above, all the H pluses are going to be plucked off by water. Water has no problem plucking those off. But when we get to the weak acids, then it's a little bit more difficult because let's say the ladder only goes this high. And so this person has to jump up and grab this apple here. You know, it's still doable, but it's going to be harder. And so it's going to be more and more difficult the weaker the acid is. And so do you think the person's going to clean off all these? Maybe they'll get a few, you know. But as we get higher and higher, then this is water. Water is going to have a harder and harder time plucking off the hydrogens. And so the leveling effect is like this. All these are going to have the hydrogen ion cleanly plucked off. So this is the cause. It doesn't matter if it's perchloric or nitric. It's below a certain level, and so there are going to be no apples left here. And then as it gets a weaker, then there are going to be fewer and fewer apples plucked from the tree the higher we go up. And so the same thing. Here, yeah, we'll pluck off some, but not all. But as we get lower and lower, there's going to be fewer and fewer hydrogens plucked off by water. That's a side trip to the leveling effect. What were we talking about earlier? Yeah. Well, we were talking about the acid chart. What's the difference between a strong acid and weak acid? That's it, the difference. The difference is how easily water can take the hydrogen ion. But it doesn't have to be water, it could be anything. You know, it doesn't have to be water, how easily the base can. And so there are things more powerful than water, things that are more powerful than water can start plucking these ones off. And then there are things that are less powerful than water. And that would just be a relationship to the height here. So let's take a look here. Lithium ions. Lithium ions. Do you see lithium ions on the acid side? This is the acid side. No. You know what's next to the acids? Called these, the bases here. These are actually called the conjugate bases. So if HClO4 loses a proton, what's left is perchlorate. And so if the acid is strong, the base is extremely weak. If the acid is strong, the base is weak. Why? Because the acid loses the H+ easily. that means the base is going to gain the H plus. Maybe it doesn't want it so much. Whereas if the acid is weak, then that means it holds onto the hydrogen ion more tightly. And so something like this holds onto it more tightly, therefore it's going to have an attraction to the H plus base. And so if we take a look for lithium ion doesn't occur on either side. So what we're going to say is maybe, this chart's not comprehensive enough, or maybe it just doesn't react as an acid or base. And so let's think about lithium ion. Is lithium ion a good hydrogen donor? Is there any hydrogen in lithium? No. Is it a good hydrogen acceptor? Acids are hydrogen ion donors, bases are hydrogen ion acceptors. No, lithium ion does not want an H plus. They're both positively charged. They're going to repel each other. So we'll call it neutral. N for neutral. This is a different neutral than this. For example, water. Do you see water here? I see water here. Water is a base. So water is a base. But I also see water here on the left side. Water is also an acid. Here. And so water is interesting because water is both an acid and a base. When something can act as both an acid and base, we call it amphoteric. There are a lot of amphoteric species, but water is interesting in that it doesn't matter which way it goes. It could go acid just as easily as it could go base. Other amphoterics have a preference. So for example, hydroxide. If we look at hydroxide occurs on the acid side and it occurs on the base side. But normally when we think about hydroxide, we think of the hydroxide as being a strong, turns out we think of it as being a strong base. In fact, it is a strong base. Hydroxide is a strong base. And in terms of acid, it's so weak, we don't even really consider it an acid. So this is amphoteric, but its amphoterism is heavily biased towards hydroxide being a base. The same thing with ammonia. Ammonia is amphoteric. Here's ammonia as the acid. There's ammonia as the base. And so as an acid, it's extremely weak, but as a base, it's moderate. And so ammonia is a moderate base. That's typically what we think about ammonia. However, it could go either way. It's just heavily biased towards the base end of things. Water is not heavily biased one way or the other. So water is often thought of as neutral. However, it's not really neutral. Water can act as an acid, or water can act as a base. It can react as both, either way. How about sulfite? If we look at sulfite, I don't see it here. I see sulfate. Do you see sulfate? Here. There's no sulfite. And so that means one of two things. One, sulfite is neither an acid nor base. Or two, my chart is too not comprehensive enough. A little too abridged in the sense that it's missing. And so what do you think? Do you think sulfite belongs here, or sulfite should be neutral, like sodium ions or lithium ions? And so if we look at a more comprehensive chart, we do have a more comprehensive chart here. And that's that chart in the back corner there. And sulfite is actually on the second column, it's midway up. And so it's a moderate base. Sulfite is a moderate base. We can think of it because being a moderate base because we have hydrogen sulfide ion and sulfurous acid. How do you form hydrogen sulfide? You take sulfite and give it an H plus. So it accepts an H plus, making it a base. How about sodium ions? Sodium ions are like lithium, is neutral. How about phosphate? Now phosphate's on our chart here. Are you going to see phosphate on the acid side? No, because it's missing what? Hydrogen. There's no hydrogen. but we can see phosphate on the base side. In fact, phosphate is here. Would we call phosphate a weak base or a strong base? Phosphate's considered a weak base, but it's borderline. You see phosphate's right next to hydroxide? It's a borderline strong base. But still, it's just going to be a weak base. So this is a base. It's not going to be on the acid side because there's no hydrogen. And so in this case, we need to pick the strongest acid present. Well, there's only one acid. What is it? Water. There's only one acid present, it's water, so will be our acid. Now we have three bases. Out of these three bases, which one's the strongest? So, go back here. Okay, so let's start off here with the strongest base. The strongest base here is called methine. These are very powerful bases. Does methane want to lose a hydrogen ion? No, it doesn't. No, this is a molecule. This is not an ionic compound, so it really doesn't want to lose a hydrogen ion. But if it does, it forms methine. Methine is terribly unhappy compared to methane. Does hydrogen want to lose a hydrogen ion? No. This is hydride, methyl hydride oxide. You know what NH2 minus is called? Amide. NH2 minus is amide. Amide is the strongest base on that chart over there. So this has three more bases. So amide. Sulfide's a powerful base, and then hydroxide. All these are powerful bases. And then we get the weaker bases. And so let's take a look at the bases that we're comparing. Water, sulfite, and phosphate. Well, phosphate is borderline strong, and then sulfite is, based on the chart over there, is somewhere in the middle here. And then water is way up here. And so it looks to be the strongest base we have is phosphate. And so the strongest acid is water, the strongest base is phosphate. And all we need to do now is just react them together. Okay, we react them together by transferring a single proton, single H plus from the acid to the base. And so transfer an H plus over here. And so we're going to lose an H plus. If water loses an H plus, all that's left over is an OH. The OH is going to have a negative charge. And then H plus is going to combine with phosphate, making HPO4. What's the charge on that? Yeah, 2 minus. And so this is hydroxide, and this is called monohydrogen phosphate. Hydroxide is both an acid and a base. How about monohydrogen phosphate? Turns out monohydrogen phosphate is both an acid and a base. So here's monohydrogen phosphate as the acid, here's monohydrogen phosphate as the base. It clearly looks like a better base than it is an acid, because it's close to the strong. This is pretty far away from the strong acid. So it looks like a better base than an acid. So monohydrogen phosphate should be a better base than an acid, but we don't know how it's going to react because it depends on what we react it with. The amphoteric species, we don't know. Is it going to act as the acid or is it going to act as a base? Well, it depends. What are you reacting with? And so in this case, what we're going to do is we're going to figure out which way this reaction should go. In other words, we've got to figure out the downhill direction. Is it going downhill forward or is it going downhill reverse? In order to look at the reverse let's see, we're going to go and take this reaction backwards. If we take this reaction backwards, then we are reacting hydroxide and monohydrogen phosphate. And so which of these two will be the acid? Monohydrogen phosphate will be the acid. How did you know that? Yeah, because it's losing the hydrogen. Did we use this here? This said that monohydrogen phosphate should be a stronger base than an acid because monohydrogen phosphate is here and the strong acids are way up there. No, we don't pay any attention. We just look at how it reacts in this reaction. And then hydroxide will be the base. Then we have to determine the driving force. What is the driving force for acid base? The driving force for acid base is going from stronger acid to weaker acid. And so let's compare the two acids. The two acids are water versus monohydrogen phosphate. And so water versus monohydrogen phosphate, which one's a better acid? Monohydrogen phosphate. So monohydrogen phosphate is stronger, water is weaker. If the acids do this, then the bases must also follow. And that must mean that phosphate must be a weaker base, hydroxide a stronger base. Is that correct? Yeah. Phosphate's a weaker base, hydroxide is a stronger base. That is correct. And so what we see here is this. We're going from weaker to stronger, which means that going forward, it's uphill. It's uphill. And that means that, it doesn't want to react. It should stay as reactants. In fact, there's no driving force. If it's going uphill, we're going from more stable to less stable. Is that favorable? No. And so typically what we say is this: no driving force, no acid-base reaction. No driving force, no acid-base reaction. But pretty soon we're going to, that's too black and white, right? For me, that's a little too black and white because how big of a difference is this in terms of strength? In other words, is monohydrogen phosphate significantly stronger than water? No, they're almost at the same level. If they're almost at the same level, then this is what happens. It's not a steep hill to climb. It's a very gentle hill to climb. If it's a very gentle hill to climb, then what that means is this. It means that mostly we're going to have this. But we might have a little bit of this because there could be some energetic enough molecules that can climb the hill by reaction. Does that make sense? And this is what we call, in chemistry, this is what we call a dynamic equilibrium. A dynamic equilibrium means a little bit, of product can actually form here. A little bit of product. And so even though I don't expect driving force, it's not such a huge difference. Such that I'll expect some product to form. Does that make sense? Where did we see that before? Where we saw that before is ammonia. When we think about ammonia, is ammonia ionic or molecular? Ammonia is molecular. And so if we're dealing with molecules, do you automatically think metathesis? No, metathesis deals with ions, not molecules, not elements, ions. But you have to train yourself. If you see ammonia, there could be ions. How could there be ions in ammonia? This is from Thursday, last week. Yeah, right. What happens is ammonia can react with a little bit of water. Ammonia is a base, water is the acid. And what forms here is, acids are going to lose the hydrogen ion, bases are going to accept it. So we're going to go from NH3 to NH4. And then we got to up the charge. It's going to be NH4 plus and hydroxide. Now, going backwards, which one would be the acid? Which one would be the base? Going backwards. Ammonium, does it lose or does it gain going backwards? It loses, so this is the acid. The acids lose a proton, and the base would gain. And so what we're trying to do is we're trying to figure out, which is it? Is it downhill forward or downhill backwards? And so we compare the two acids, water versus ammonium. So here's water, here's ammonium. Which one's stronger acid, water or ammonium? Ammonium is a stronger acid. Water is a weaker acid. Water is a weaker acid than ammonium. That means the bases must follow. And so that must mean that ammonia is a weaker base than hydroxide. Well, here's hydroxide. Ammonia is here. The strongest bases are at the bottom. The strongest acids are at the top. And so this means that hydroxide is stronger than ammonia. So this is stronger, this is weaker. And so that means it's uphill this way, right? It's uphill this way because these are less stable, these are more stable. Does that make sense? But, how big is this hill decline? It would be a huge hill decline. Let's say we're comparing water with perchloric acid. If we compare water with perchloric acid is way up here, water is way down there. And so it'd be this is steep decline. Right? But if we're comparing not with perchloric, but if we're comparing with ammonium, it's not so steep. Or if we're comparing with monohydrogen phosphate, it's almost level. And so that makes a difference in this. And so what happens is, yes, it is a hill decline, but it's not an insurmountable hill. That is, there are going to be a few energetic enough molecules to make it over this. Because not every ammonia molecule is identical, like here. Even though this water is at 25 degrees C, is every single water molecule moving identically with the others? No, what we're going to see is some are going to be more energetic, some are going to be less energetic. The more energetic ones will actually evaporate off the surface and escape. And so not every water is going to have, they're all the same, they're water, but not every water is going to have the same energy. And so even though, yes, this is not favorable, we expect no reaction, well, the hill's not that steep, so some of these can actually make it to product here. And so what we say is we say a little bit of this forms, and the way I showed this is by drawing two uneven arrows. The downhill direction is this way, but the uphill is not insurmountable. The uphill maybe a little bit can make it uphill. Does that make sense? And so this is the uneven arrows. This is called a dynamic equilibrium. Here. In this case. And so, yes, ammonia and water, we look for metathesis reactions because ammonia reacts with a little bit of water to form some ions. And these ions, ammonium ions and hydroxide ions, will react with metathesis. So, but the end result is that we have no driving force here. And we expect no reaction for acid base. But are we looking at all acid base? No, we're only looking at Bronsted. There could potentially be a Lewis acid base, but we're not going to go there. We're just looking at Bronsted. So far, yeah, even though I say no reaction, there could be a little bit of reaction here. In fact, I do expect a little bit of reaction, but it's not favorable in the sense that it's a downhill trip to product. So if it's not metathesis and it's not acid-base, then what is it? It's got to be redox, because there are only three basic types of reaction. And so how do I deal with redox? Well, redox follows the same procedure as Bronsted acid-base. The only difference is the chart. Is more complicated, this chart here. Redox are known as electron transfer reactions. Bronsted acid-base are proton transfer. But when we look at the electron transfer, 2 electrons transferred, 5 electrons, 6 electrons, 4 electrons, 3 electrons. The number of electrons varies, 1 electron. And so the reaction is a bit more complicated. And so we'll talk about redox a little bit later. So I'm going to come back to redox. And so we'll revisit this problem a little bit later. But the thing we want to know is we want to actually kind of try to predict, if we expect any redox, based on our knowledge of these species here. It's tough to do initially. All right, so let's try, before we do that, let's try some acid base. Now, there's some overlap with metathesis. We already did this reaction for metathesis, or did we? Phosphoric acid. What's the formula? H3PO4. Sodium hydroxide? And AOH. And we did this. What did we form? In metathesis, what we formed is H and OH. H and OH makes water, and Na and PO4. Na and PO4 makes sodium phosphate. So what we formed is water and sodium phosphate. Do you guys have this one already in your notes, right? It was either with sodium hydroxide or potassium hydroxide. I can't remember. But you should have it. Did we do it?
Yeah.
Okay, good. It's a metathesis reaction. But, these are acids and bases as well. And so there's overlap. But if I treat this as a Bronsted, I do it differently. Yeah, I do it differently. This is the way I do it. First, we inventory. When we inventory it, we're going to inventory it in this way. We look at what water is going to do. And so H3PO4, is that a lattice type structure or is that molecular type structure? H3PO4. Lattice? Do you agree? Lattice structure? If this were Na3PO4 or Li3PO4, yes. If this were metal and the non-metal, yes. But this is an acid. When we're dealing with acids, all the acids are going to be molecular structure. It's all non-metals, H. And so this is a molecule. We know water is capable of plucking the H off what acids? The 7 strong acids. Water is capable of plucking the H cleanly off. But what about the weak acids? No. And so since water is not capable of plucking the H off, then what we expect to see, these are the major species. We expect to see mostly H3PO4 molecules. But you got to remember, H3PO4 is one of the lower ones, one of the lower weak ones. And so some of the H's could be plucked off, right? And so therefore we're going to call this the major species, because the major species, most of them are not going to be plucked off. Most of the apples are going to be left on the tree. It's a little too hard. And so water can try to pull these off, but it's going to have too much difficulty. It's not a strong acid. Strong acids lose the H plus easily. Weak acid will give a lot more trouble. How much trouble depends on how weak and how strong, but here we're just going to do it black and white. Either it plucks it off or it doesn't. As a weak acid, it doesn't pluck it off in total. But in reality, a little bit gets plucked off. How about sodium hydroxide? Is that a lattice structure or molecules, or what is it? Sodium hydroxide, metal and non-metal forms the salt. The salts are typically molecules or lattices. Which is I look to you. This I showed before. This is potassium hydroxide. Sodium is a little bit smaller. But what is this? Molecules or lattice? That's a lattice. And so the way lattices dissolve in water, are the lattices broken apart or does it stay together? It's broken apart. And so what does it break apart into? Into ions? What are the ions? Sodium ions and hydroxide ions. All right, and then there's one other major species missing. What is it? Water. And so we go down our chart. When we go down our chart, phosphoric acid is a acid. It's not amphoteric. This one's only going to occur on the acid side. Sodium ions, not applicable, neutral. Hydroxide, base. Clearly, it's a much better base. It's one of the strong bases, but potentially it could act as a acid. Not all that likely. Water, acid, base, either way, it doesn't matter. Water, go either way. It doesn't have a bias, whereas hydroxide definitely is biased towards strong base, because it is one of the strong bases. In fact, if you ask anybody, name a strong base, they're going to say sodium hydroxide. All right, then we look for, we have 3 acids here. Which of these 3 acids is the strongest? I think you don't need the chart for this one.
Water.
Because what would you rather have, phosphoric acid or water? Which one do you think is a stronger acid? And then hydroxide is typically a strong base, not even an acid. And so I think the strongest acid is going to be phosphoric acid. Well, what's the strongest base? Hydroxide. And so the reaction here is this. And so we do it quite a bit different. If we do this metathesis, what we do is full reaction. We react all 3 hydrogens. If we do Bronsted, we only react 1 hydrogen. And that is, the acid loses 1 hydrogen to the base. So H3PO4 plus hydroxide. This is our acid, this is our base. So the acid loses 1 hydrogen to form H2PO4. What's the charge on H2PO4? 2 minus. And then hydroxide gains an H, so it forms H2O. And so when we do this as a Bronsted acid base, we only react 1 of the hydrogens here. There's still 2 left that could potentially react. But we'll stop here and then take a look at this step. If we go backwards, which one's the acid? Well, both of these are amphoteric. Both of them can act either as an acid or base. The only way we can tell which one is which is by looking at which one loses going backwards. Which one loses? Water. So this is my acid. This contradicts what the chart says. If you look at the chart, this chart, by the way, is on Piazza. If you look at the chart, which one's a better acid? H2PO4 2 minus or water? H2PO4 minus or water? Which is a better acid? H2PO4 minus. But it doesn't matter what the chart says. What matters is what the reaction says. The reaction says that it's not H2PO4 minus that's going to be the acid, it's going to be water. H2PO4 minus in this case will be the base. All right, then we compare the 2 acids, H3PO4 versus water. Which one's stronger, H3PO4 or water? H3PO4. So we're going from stronger to weaker. And here, there's a pretty significant difference in strength. There's water way down here. Where's H3PO4? Way up there. And so when I look at this, H2PO4 is much stronger than water, so this is going to be steep downhill descent. We expect to form a lot of this. That must mean hydroxide is a stronger base than H2PO4, and that's correct. That follows. And so what we have here is we have a driving force for forward reaction. We're going from stronger to weaker acid. Does that make sense? All right, now, if there is more hydroxide left over, then the hydroxide can attack what remains. If there's extra hydroxide around, then it can attack either this or this. Which one should it attack? If there's extra hydroxide around, it'll attack what we just formed. This is what we just formed. Which should the hydroxide attack? This one or this one? It's going to attack the H2PO4 2 minus. Why? It's because this is a stronger acid than this. But didn't we just call it a base? We did. In fact, it is a base here. But if there's extra hydroxide around, its role changes depending on what it's surrounded by. And so that's what I mean by this statement here. What I mean by this statement is repeat to determine if further reaction occurs. In fact, when we did the metathesis, we reacted all three hydrogens. We reacted all three hydrogens, and we ended up forming 3 waters and phosphate rather than dihydrogen or monohydrogen phosphate. Phosphate. But this is the Bronsted approach, and leave it at that. Okay, we'll take a break and then we'll try this next one here.